Hi everyone, welcome to this virtual IoT meetup. My name is Frédéric Deviens, or Frédéric Debian if you want to pronounce it in English. I'm the new IoT and Edge program manager here at the Eclipse Foundation, and it is my pleasure to be your new host for this virtual IoT meetup. Thank you so much for joining today first. So before we get to our presenters, I simply wanted to share with you a few elements of news that are happening in the Eclipse IoT world. So first, as you know, we just have completed our IoT developer survey. So if our cameraman can show my wonderful slide here, you will see essentially that we've got more than 1,700 responses for this year, which is 3 times more than 2019. Then that we have more than 700 complete responses for this. Oh, and I didn't share the right screen, so that is my mistake. So let me correct that. Yeah, that would be helpful to share the right screen. Okay. Hey, growing pains there. All right. So we've got more than 709 complete responses there. So that's twice more than 2018. And we've got several of our contributors in the Eclipse community that had collectors for the survey on their websites and properties. So the IoT working group itself, Bosch, Cirrus Link, and this virtual meetup have been top contributors in responses for the survey. So thank you very much for that. So now, in the next few days, I'll be hard at work trying to synthesize and analyze the results, and we'll come publicly with the results published on Eclipse IoT websites, Eclipse websites on April 1st. So look forward to that. Another thing I briefly want to tell you also is that we have completed the program for our Eclipse IoT Day at the IoT World Conference 2019. So this will be in Santa Clara in the month of May. And the IoT Day is on May 13. The conference itself is after that. So we've got a very, very interesting array of speakers and presentations. So you can access speaker bios and registration information, as well as the agenda for the IoT Day on the website. So you see it on the broadcast right now. So please have a look, and I look forward to meet with at least some of you during our IoT Day in Santa Clara. So that's it for that. Now, the main reason why we are here, I have the pleasure to introduce Wes Johnson and Chad Kinley from Cirrus Link Solutions. So Chad and Wes, it's your turn now. Please go ahead with your presentation, and I'm looking forward to be back at the end to answer, well, read you the questions from the audience and moderating the conversation there. So Chad and Wes, it's up to you now.
All right, thank you. So today we're going to go over Sparkplug and Eclipse Tahu and how it affects and can affect IIoT. So my name is Wes Johnson. I'm VP of Software for Cirrus Link Solutions. Been with the company for a little over 5 years now. I actually started in automation and SCADA and IIoT, depending on what time it was and what it was called at the time. Since 2004, I started working at Arcom Solutions with Arlen Nipper, who is one of the 2 co-inventors of MQTT. It was at Arcom where I started working with MQTT and also started and led the what later became the Eclipse Kuro project, and also Eclipse Kapua as well. So since leaving Eurotech, I've begun working on Sparkplug and what is now Eclipse Tahu.
And my name's Chad Keenley. I'm the principal software engineer at Cirrus Link Solutions. I've been developing IoT and embedded software for over a decade. Years ago at Eurotech, I worked with Wes and was one of the original creators of what is now Eclipse Kura. And I'm currently a project lead on the Eclipse Tahu project.
All right, so this is the agenda for today. So we're going to go over some history. I assume that most people that are watching this now already know what MQTT is or have at least heard of it because it's become so prevalent in the industry. But I think there are a lot of things that people don't know about MQTT that we'd like to shed some light on. Also, we're going to cover what the Sparkplug design concepts were. So what was MQTT lacking that we needed or wanted to define to be able to solve real world problems using MQTT? Then we'll go over the Sparkplug technical details. So what are the finer details of how it's put together and how it works? Then finally, Chad's going to do a live demo and show some of the commercial products that we have available that utilize Sparkplug underneath. And then at the very end, we'll do a Q&A. So this is sort of a timeline of MQTT and Sparkplug as well. So in 1999, Arlen Nipper, who is Cirrus Link's president and CTO, co-invented MQTT with Andy Stanford Clark of IBM, who's still at IBM as the CTO of IBM UK. So the project was actually a specific project to do oil pipeline monitoring for Phillips 66. So I'll come back to that because a lot of things that we do with MQTT and Sparkplug were actually initially conceived with that original project. So then, as I said, in 2004, I began working with MQTT and also started what was internally branded as the Eurotech Software Framework, or ESF, after Archon was acquired by Eurotech. That later then became an open source project within the Eclipse Foundation. During that time, we did a lot of projects for various customers within various industries, most prevalently probably in oil and gas. But really MQTT wasn't taking off as a protocol in the way that it did after 2011. So there was a blog that was posted by one of the Facebook developers, and they had started using MQTT for Facebook Messenger. And so one of the reasons that they actually selected that and was talked about in this blog was that they wanted to use MQTT for its low power capabilities. So because most people were using Messenger on phones, because of the way that MQTT was optimized for bandwidth, it affected battery power consumption on a phone in very much the same way, and that is not very much. In 2012, the Eclipse Tahu project was open sourced within Eclipse. So Tahu is a open source MQTT client library, so a lot of implementations of MQTT. Chad, who's going to be doing the demo, is actually one of the initial committers on that project as well. In 2014, it became an OASIS and IEEE standard. Then later on, Cirrus Link partnered with Inductive Automation, where we really wanted to formalize what is now Sparkplug, or at least begin the formalization process and opening these ideas to the community at large. So one of the things that happened with Cirrus Link at that time was that we had found a partner in Inductive Automation who created a SCADA platform that we could use many of these ideas in and actually create usable functional products with. So what is MQTT? Again, a lot of this is probably review, but it's based on TCP/IP, which was done very intentionally at the time. So TCP is a stateful way of communicating over an IP network, unlike UDP. So one of those initial ideas was if we're going to have a stateful protocol, then we want it to use a stateful socket connection, which was already implemented in TCP. And so Andy and Arlen didn't want to reinvent a stateful protocol on top of UDP, for example. MQTT itself doesn't actually stand for anything anymore. Originally, MQ stood for message queuing, which came from the IBM MQ series product line, and the TT was for telemetry transport. Andy actually last year corrected me because the Wikipedia page said that it did still stand for that. It no longer does. It's just an acronym that technically has no meaning. So the main 4 points of MQTT are that it was simple, efficient, stateful, and also Andy and Arlen made a strong push for it to be open, which was sort of a new concept, certainly for IBM and also for Arcom at the time. All right, so simple anatomy of MQTT and how the different parts interact. So there is a server and there is a client, and a client can establish a connection to that server. So that connection is outbound, and that the client makes an outbound TCP connection to that MQTT server. Once it's connected, because it is in an open socket at that point, communication is bidirectional after that connection occurs. And that's an important point to make. It works sort of like WebSockets in the sense that that session is established and communication can go in either direction at that point, even though it's initiated by the client in that initial connect. From there, clients can publish or they can subscribe to messages. And so other clients can also connect to the MQTT server, and you can connect as many as you want, as will reasonably be handled by the MQTT server implementation. So in one way, you can think about this as the way an old PBX or telephone switchboard works. So the MQTT server acts like the switchboard operator, although there's a very important difference and distinction. So normally in a switchboard telephone context, that operator is connecting calls. And so really it's just tying single callers to other single callers. In this case, the MQTT server is tying messages to clients, and the relationship is not one-to-one, and it's not client-to-client. Instead, messages can go into the MQTT server and then get routed to other MQTT clients that are subscribed on that specific topic. So it's routing of messages rather than clients. All right, so here's a typical MQTT message flow. So one client connects, another client connects, and then one client, for example, can subscribe on a topic. And in this case, that client is subscribing on hash. So within topics and how those messages are routed, there are some notions of wildcards in MQTT. So hash is one of those, which basically says, I want any message that goes into that MQTT server to be delivered to me. And so this client then could publish a message. And in this case, that topic is hello/world. It's slash delimited, also never begins with a slash. And then the payload is hello from a client, just an ASCII text. So that message goes into the MQTT server, and the MQTT server maintains a internal map of the clients and all of their subscriptions. So it has an internal subscription table, and it sees this topic or message come in with this topic, and then knows that this other client had subscribed on hash and therefore needs to receive that message. So that message then gets delivered to that client and any other potential clients that have subscribed. And so in this case, even though from an MQTT standpoint, we treat all clients equally, clearly in this particular message flow, they're not. There's a producer of data and there's a subscriber of data. And this is more typical of how one would actually use MQTT in a real IIoT solution. So this is what MQTT does, and we needed to look at what MQTT does for us in order to design what we wanted to with Sparkplug. So basically, what was MQTT lacking? So clients connect to a server, and once connected, they can publish and subscribe. And so this is very important within the context of IIoT, because typically you wouldn't want outside connections coming down into your operations center. So for example, you wouldn't want edge devices out on an oil pipeline that had open sockets that could receive connections from somewhere else. Also within a factory, you wouldn't want open sockets through that firewall to allow connections from somewhere else. So if you look at things like the Purdue model, which are very common topics within IIoT today, MQTT does a really good job of taking data from that level 3 or operations center through that firewall, because it's outbound originated. But then again, once established, it's bidirectional. So you can still, if you want to allow commands to come back down to write to outputs, for example. So MQTT also defines the primary message components. So the three important ones are the topic, which is used for message routing, the payload, and also the quality of service. MQTT certainly defines a lot more than this, such as retained messages and last will and testament, and how sessions are persisted with regard to keep alive. But in terms of the basic components of a message, topic, payload, and quality of service are the most important things. Again, topics are / delimited strings, and those are used by routing of messages by the server to and from clients. So the MQTT server doesn't know or care about the payloads associated with a message. It cares about the topic, so it can route those messages to the appropriate subscribers. And it also cares about the quality of service, so it can deliver those messages in a way that's defined by that quality of service. Payloads are arrays of bytes. There is no schema or format defined in the MQTT specification. That was very much intentional, because obviously over time, the way that data is encoded changes in terms of popularity and in terms of improvements. So for example, XML was quite popular years ago, but it's often very verbose. So JSON is a much preferred way in most places today. But again, it just needs to be an array of bytes, and almost anything can be encoded within the digital world as an array of bytes. So there are three qualities of service. There's fire and forget, at least once and only once. And we'll come back to this because there are, I think, some misconceptions also with regard to quality of service in terms of how it's used today. All right, so MQTT is great, but if you're actually going to implement a solution with MQTT for the industrial sector in any regards, you need to answer some basic questions to be able to use MQTT in a realistic way. So again, how should clients be arranged? Do all clients produce and subscribe equally? And the answer is probably not. How are messages going to be routed to clients that need them? So this is really about defining an MQTT topic namespace and how those topics get arranged. So does it make sense to just specify who it is that's producing the data? So in the example here, an edge IP address, and then whatever that sensor value is, or whatever that output might be. And maybe that's okay, but there might be some better ways to do it. What quality of service should we use for IIoT applications? And for example, is QoS2 always preferred because it's guaranteed and it'll only get there once? And again, the answer is probably not, and we'll go into detail a bit more on that. What schema or format should be used to encode the data? Can we just use JSON and call it good? What about security? Well, it's probably okay because it's binary, so nobody can read it anyways, which obviously is not a good approach. And are there other things we could do to make it more efficient? So should we look at compression, or are there ways that we can optimize data within the payload to make things more flexible? All right, so these are the ways that we answered a lot of these questions in the Sparkplug specification. So With terms of client arrangement, we really determined that there are two basic types of clients. There are edge clients, which are those producers of data, but also often have outputs associated with them as well. So those edge clients are the things that communicate directly with your I/O. So PLCs or RTUs or whatever the case may be. And then there are backend clients. So these are things that receive that data and also potentially control those outputs associated with the edge clients. So these backend clients can be things like a SCADA host system or a historian or a cloud provider, for example. Then how are messages going to be routed to the clients that need them? So what we did in Sparkplug was we really identified a hierarchy of data associated with who the data is coming from. So the topics are arranged by what we call group ID, edge node ID, and device IDs. And so this gives us a well-defined topic namespace, which allows us to make some assumptions at a host system or a backend client when data arrives. So we know who the data came from, but we don't necessarily know what the data is. So we left that what of the data in the payload itself. So the topic really determines who, the payload defines what. Then what quality of service should be used for IoT applications. And using QoS2, even though it may sound the best, isn't really. So in the case of, say, a control system where maybe you want to open a valve on a pipeline, for example, it probably only makes sense to open that valve right then. So typically, opening or closing of a valve is associated with a much larger complex sequence of events. And let's say that we publish a message at quality of service 2 to open a valve. And then let's say that that MQTT server goes offline, which can happen for all sorts of reasons. And let's say there's some period of downtime, then after a while it comes back online. It still has that QoS2 message sitting inside of it, and it's obligated at that point to deliver it. And then the valve may open in at a time when you really don't want it to. So we really need to think about quality of service in terms of real world applications and what that delivery should look like. QoS2 within a banking scenario where somebody might withdraw money from a checking account, it certainly makes sense because you certainly want that transaction to go through. But within industrial applications, that's not necessarily the case. So then what format schema for the data should we use? So this is a debate that still probably lingers on, but we decided to use Google protobufs for the encoding mechanism. So it's a binary encoded payload format, which really packs data in a very efficient way. And also it has and continues to have good library support. So using a bit of code and open source reference implementations from Tahu, it's actually pretty easy to take that data and either encode or decode it and then convert it to JSON or other more heavy but user-friendly things at either end for display and consumption and debug and that sort of thing. So then what about security? So security is always important, always required, but outside the scope of Tahu. So just like MQTT really left MQTT up to the implementation, Tahu does the same thing. So MQTT was intentionally agnostic to how security was implemented because it was expected, and correctly so, that TCP/IP would support different, newer, and better security schemes throughout its existence, and that has continued to be the case. So if you look at the history of SSL, the TLS, and OAuth, and other new contemporary and better security schemes, those are all still supported by MQTT and also Tahu. So again, are there other things we can do to make it more efficient? So we added support for the notion of aliasing within the payload. So this is very similar to how MQTT 5 supports aliasing for topics. So if you have a topic, why would you have to send the full ASCII string every single time when you could give it a much smaller representation of that topic and still mean the same thing? So within the payload, we do that for what we call metrics or tag names, the things that represent the real I/O points of a system. We also added support for metadata, complex data types, multi-part messages, historical data, and others. All right, so this is one of the first of, or the first of a few more significant concepts that we put into Sparkplug. So this is really the idea of how we could use a stateful session to our advantage. So many current MQTT solutions on the market today don't actually take the stateful session into account. So for example, let's say that there's a basic IoT device that has a temperature sensor, and many solutions would just take that MQTT message and publish it up periodically. So maybe every minute, or maybe every 10 minutes, or just periodically. And that data will typically get sent whether it's changed or not. And so if you send the same value every minute, you're really not utilizing the stateful session of MQTT in a way that it could be used. So what we did was defined what a session is. So an MQTT session is bookended by a birth and a death message. So a death message, or a last will and testament within MQTT, was something that was already part of the original design. And again, very much intentionally, because this same concept was really part of the original Phillips 66 project from 1999. So what we can do is create that session in the birth, publish all of the data that we know about. So every tag, every IO point that we're responsible for, we're going to send that up to the MQTT server, and also state what all of their initial values are, or all of the values that were correct at the time of that birth. From that point on, we don't have to publish data periodically. We only have to publish it when it changes. And the reason is that if that session is still established and it's never gone down, and the edge device knows what a change is, then it will publish up that new value when it changes. And so at the back end or consuming application, then you always have what that current value is. So in Sparkplug, we always publish data. So what we call data messages and also command messages, these are always published on QoS 0. And the reason is we know that that session is established. QoS 0 is good enough for us to be able to get that data across. And also in the case of writes that go back down to the device, we'd never get in that situation where we're opening a valve at a time when we didn't mean to. So again, as long as that session remains established, then we only have to publish on change. And so how do we determine what a change is? For a Boolean, typically that's pretty obvious. If it goes true to false or false to true, that's a change. For floating point values, it can be a little bit more difficult, but certainly deadbands can be implemented on the edge to denote what a change actually is. And again, those are typically application-specific things. So the most common question is aren't there holes in this? And the answer is yes. There's really one. So we use the concept of what we call a primary host ID, which basically allows a primary host or a backend host application to notify an edge client that it is online and listening to that remote edge device. So that in conjunction with the MQTT Keep Alive timer, we can denote that that end-to-end communication is always there. So there is one scenario in which we can actually lose this session in a ungraceful way. And that is if an MQTT client were to lose its connection without a socket actually being closed. So an example of this occurring would be, say, that you're a mobile cellular device and you move out of cellular coverage. You won't see a socket close. Instead, you'll just see that that socket is still open and data cannot flow across it. And so it may be that you would have attempted to publish some data messages from that edge client up to a central gateway. In that scenario, you can lose data, but this can be handled with implementation. For example, you can keep a rolling buffer of the last known messages, and you also know that because of MQTT and how keep alive timeouts work within MQTT, that the maximum time period where this can occur is 1.5 times the keep alive timeout. So in typical applications, your keep alive timer might be 30 seconds or 2 minutes or even 5 seconds. So the window of data in which you could lose is quite small, and also because Sparkplug supports historical messages, if that ever were to occur, you could still historize that data and send it up at a later time. So the main purpose of all of this was really to reduce the amount of bandwidth that was used over the network. So again, because we're only publishing on change, we're not polling, we can only publish the data when it's required. And as a result, depending on the system, you can see significant improvements in total bandwidth usage. Also, if you do talk to a legacy device, for example, which is very common for us, we can do that polling at the edge really, really quickly. And then whenever we see that data change, then we can publish that change value. So you might have a lot of bandwidth being used locally, but that's typically over a much higher speed network. Then you can publish the data over your low bandwidth network, but in this much smarter way. All right, so next major concept was source of truth and dynamic discovery. So we wanted to be able to allow back-end consuming client applications the ability to not have to be configured every time something was modified on an edge device. So for example, if we look at data that might be associated with polling of a PLC. So in this picture on the right, that's actually a electronic flow meter used for measuring flow on a pipeline. So you might have a Modbus device that has an address of 40,027 and it has a value of 1256. So what does that 1256 represent? Is it a raw value, or is it scaled? Are there engineering units associated with it? Is there a range? And really just what is that data? So typically the way that this would be done in historical SCADA systems is that data would then be entered in by hand manually into the SCADA system. If you wanted that data to also go to a historian, you would then enter that data again on that system. If you wanted to go to cloud, you would have to again represent that data from this raw sort of meaningless data to what it represented in the real world. So hypothetically, if this 1256 value actually represented a temperature and 1256 was a raw value from 0 to 4095, and it actually represents the temperature in degrees Celsius, and its range is from 0 to 100. If we were to convert that, we know that really this is a temperature value of 30.1 degrees, which is a much more realistic thing to know either in your SCADA system, in your historian, or in a cloud consuming application. So if we assume that that's the case, that was how it's configured, we could set that information up on the edge and then denote that in our MQTT publish up to the consuming applications. So now they all can automatically discover what it is that that value represents without ever even having to know what the Modbus address was or that it was a scale value. another good use case for this is that you might go in and say your temperature sensor breaks, or you want to get a bigger range. Say now you put in a new temperature sensor, and that value now represents a temperature of 0 to 150 degrees. So now, even though you're getting the same value of 1256, it's now representing a new temperature of 46 degrees because the scale has changed. And so what we can do is change that value on the edge. And that was done at a time when somebody was physically touching the unit, knew what the real world meaning was of that data. And as a result, it could automatically be consumed by any other backend clients that needed it. All right, so the other thing that we really wanted to support was failover, redundancy, and scale. And these were all concepts that, again, were part of that original Phillips 66 project in 1999. The way that we do it in Sparkplug is slightly different and a bit more efficient than how it was done then initially. But here we can run through a few examples of how we use primary host ID and smart clients to be able to achieve this sort of thing. So we can have multiple MQTT servers, and clients can connect to any one of them at a time. So we have our edge clients down at the bottom. In this case, we're showing 2 MQTT servers. And so those edge to MQTT server connections can be over different networks. So in many of our deployments today, it's very common for us to have multiple different network paths for, again, redundancy as well. So it may be that we have one path over a wired network, and we may have another over a private cellular network, and another over a VSAT network. And so you can architect a solution in this way to provide a lot of redundancy, both at the network level and also at the server and edge level. So here we're going to walk through a scenario in which the primary host loses communication with the MQTT server. So in this scenario, that MQTT connection has gone down. So we use this notion of a primary host ID, which uses last will and testament in the server. So if that connection had gone down without an explicit disconnect, the MQTT server publishes a message on behalf of that primary host to the edge clients, and they tell those edge clients that that primary host is no longer present and listening. And so as a result, the edge clients know that there's no reason for them to continue publishing their data to that MQTT server at quality of service 0, because it's never going to go anywhere. So what they do is they disconnect from that MQTT server and connect to another one that's available via some other network path potentially, or maybe not, and to another MQTT server that is available. And so at this point, they reestablish that connection, and then they publish their birth certificates, which then let that primary host know that they're now back online. The primary host can unstale those tags because those connections have been reestablished. They know that these new values that just came in are the correct ones. And again, until some other failure occurs, these edge clients can just go on publishing data at their rate that is determined based on when the data is changing. So if we walk through another example now, so again, we're back to our everything's up and running fine scenario. We have our MQTT server, and let's say that it actually goes down. So a server crashes, or some other catastrophic failure happens with that server. All these connections then are immediately disconnected because they know that they're no longer connected to an MQTT server. The primary host is always connected to all of the MQTT servers in the network, so it remains connected to the MQTT server on the right. And again, the edge clients connect back up to it, publish their bursts, and start the process all over again. When that MQTT server comes back online, they can then reconnect to it if that is a primary path, for example, or not. So again, those are all application-specific details about what causes an edge client to walk from one to another, and if there's priority and that sort of thing. But the point is, this becomes a very resilient architecture and can be expanded based upon the number of servers, the number of different paths that you have to each of those servers. All right, so some of the technical details here on Sparkplug. So just a quick note on naming. So Sparkplug represents the specification of what it is we're describing here. And Eclipse Tahu is the open source implementation and project associated with the Sparkplug specification. So you can think about Tahu is to Sparkplug as Eclipse Tahu is to MQTT. So Tahu are the implementations, Sparkplug is the spec. Also, just a quick note on the name. So following in line with all of the other, or many of the other Eclipse IoT projects, Tahu is a Maori word, and specifically as a verb means to ignite. So that seemed like a good choice for a Sparkplug. All right, so this is what a typical architecture looks like within IIoT. So here we show the MQTT server, a number of edge clients, and a primary host client that's receiving data from those edge clients. And those edge clients are talking to either legacy PLCs or new PLCs or RTUs or other IO endpoints. So one of the primary goals with MQTT was to decouple applications, so these host clients on the left, from having to interact directly with those PLCs and RTUs. So it was to provide a more modular and pluggable architecture, so a middleware of sorts for IIoT. So again, just another quick note, because it's often forgotten or lost, but again, that data between the MQTT server and those edge devices on the right, the PLCs and the RTUs, through that MQTT channel is bidirectional. So that host client, if allowed to, can write to outputs. All right, so just a quick review of the goals. We had to define the namespace. We had to define the payload definition with metadata support. We had to define the way that state was controlled within this environment. And also we wanted to support high availability, redundancy, and scale. Also, just a quick note on Tahu, the GitHub repo URL is there as well. And also the Tahu reference implementation languages are listed there too. So what is the Sparkplug namespace? So the topic form consists of a namespace identifier, the group ID, a message type, an edge node ID, and a device ID. So the namespace is really a placeholder for defining what the definition of both the topic and the payload associated with this is. So we are currently at Sparkplug B. We actually did start with Sparkplug A, which used a different payload format that was based off of Eclipse Kura's protobuf definition. It turned out that that was far too limited for what we wanted to be able to describe within the context of Sparkplug, which is how it moved to B. And this is version 1.0 of that. The group ID is typically an arbitrary identifier associated with a group of edge nodes. So it could be a specific pipeline which has multiple different edge nodes on it. It could be a factory. It could be a regional location. It's really up to the specific implementation of the project to define what this group ID represents. Then we have message types. So I've already talked about the birth and the death. So you can have births and deaths at both the node and a device level. And then we also have data and command messages that are used within the context of a stateful session. And then we have this state message as well, which is used for allowing primary hosts to denote when they are on or offline to different edge clients. So then we have an edge node ID. Typically, this is the ID of the edge gateway. It can be a host name. It could be maybe a location within a factory. It could be a specific station location along a pipeline. Again, there's some flexibility in terms of what this is used for. Then finally, the device ID, and this is typically representative of a physical or logical device attached to and associated with the given edge node. So oftentimes this is a specific PLC or an RTU or IO device attached to that edge node. So what this gives us again is to know who the data came from. And as a result, we can make a lot of assumptions based upon this well-type definition. So in building up dashboards at central locations or tag trees, we know what to look for, and as a result, know the meaning behind these things as well. So the Sparkplug payload definition, this is based on Google protocol buffers, as I mentioned. So again, it's binary, it's compact. We've built a lot of rich metadata support into it. There is support for historical data. So when those sessions are lost, an edge client can buffer data and then send it up after reconnect, and also set this historical flag for any given tag or value change event to denote that that was a historical buffered value and not the current live real-time value. We also support what we call templates, which are basically user-defined types or complex types that you can build. So you can build more complex types that may represent a motor or other things that have specific meaning within the application that's being developed. As I mentioned earlier, we also support tag aliasing to further reduce payload size. We support binary data types and also didn't strongly type data types within the protobuf definition itself. So we use the notion of an enumeration, but again, these can be application specific depending on what it is you're implementing. And we also made it extendable. So protobufs has a built-in ability to be extended, and we implemented that in the definition as well. All right, so just a final quick note on Sparkplug state management. So in the spec, we have a number of state diagrams, like I've shown here, which show how interactions between host clients and edge clients can ensure that we do know when we're connected end to end, and also when it's appropriate to send what types of messages. So for these state messages, we actually do use the last will and testament. We also use the retain flag and quality of service 1. Using a combination of those things allows us to always ensure that edge clients are notified when an edge, when a host client goes down. We also define these message types, such as the birth and the death, and also the data and command messages, which were used within the bookends of that session. So again, data and command messages are only sent after a birth, but before a death. All right. So now getting into the demo. So I wanted to make sure that before Chad does the demo that we cover some of the basics of terminology that we use here. So there are some different terms that you'll hear due to these being commercial applications. So we'll talk about ignition. So the checkbox boxes that you see here represent ignition, which is a SCADA platform that has a number of built-in features. So first off, it has a built-in OPC server. So just a quick side note on the OPC piece. Almost all of our solutions actually involve OPC as well as MQTT. I think there's a common misconception that OPC and MQTT are direct competitors with each other. And certainly in terms of implementation, we don't see it that way. typically OPC is used for polling at the edge and then for publishing of data across a wider area network, we use MQTT. So Ignition has a built-in OPC server and also an OPC connector, and it has many different device drivers. So those device drivers are what allow the OPC server to consume data from different devices, whether they be Modbus or Allen Bradley or DMP3 or any of the other many protocols that exist. Then also it has a tag system. So what it does is allows you to take those OPC data points and push them into a tag tree that can be then used to develop dashboards and also to trigger alarms and to do many other things with the data, push it into databases, for example. So it's a modular platform which is used within operational environments to both render that data and also act upon that data that comes from these end devices. So what we at Cirrus Link have done is we've further extended the Ignition platform with MQTT modules. So these modules that we plug in, and just to cover their names, so there's transmission, which is used to take that data from that tag system of Ignition and push it into an MQTT server. So MQTT distributor is the MQTT server that runs inside of Ignition as a module. And then we have MQTT engine, which it's typically used at some central location, often a primary host application. And what it does is it receives these Sparkplug messages, and knowing the well-defined nature of that topic and also of the data that's being published from the edge is able to turn those back into tags. So what an architecture like this allows you to do is to have edge devices or edge clients where you might have a local HMI. So operators at a plant floor or at a pipeline specific location can interact with some portion of the data that they need to as an operator. But then also that data can be pushed up to a central gateway where maybe you have IT, or maybe even then you're relaying this information on to a cloud provider like AWS or Azure or IBM Watson. All of those things are possibilities here. And again, this is done via this outbound connection that doesn't require open ports at that write or OT side. All right, so this is one final slide on the demo topology. So at this point, and probably a good part of the reason that we've moved the Sparkplug specification into Eclipse is we'd already gotten a lot of interest from different OEM hardware manufacturers because they saw so much value in Sparkplug as we had conversations with these companies. So I mentioned Ignition, which comes from inductive automation, which Cirrus Link provides MQTT support for. There's also Alexis, which they have a Sparkplug enabled, what they call a director product. And so that already runs Sparkplug internally. Moxa has a platform called Things Pro, which their edge gateways communicate with, and that also internally uses Sparkplug. Easy Automation manufactures PLCs, amongst other things. They have a PLC that actually natively supports Sparkplug, so instead of interacting with it via Modbus, it can actually generate Sparkplug messages natively on its own without an edge gateway actually being present. Opto22, Advantech, FreeWave, these are all other companies that are supporting Ignition Edge, but also are doing some other Sparkplug implementations on their own. So these are some of the devices that Chad will be going over in his demo, and this is sort of the basic architecture of how this is put together. Also, there are 3 MQTT servers, which he'll show with some of that failover support that we talked about, and also that central Ignition gateway where he'll show some dashboarding as well. All right, so with that, over to you, Chad.
Thank you, Wes. My screen should be sharing. All right. So starting off with that last diagram that Wes showed, what I've got set up for this demo is I've got an ignition gateway in EC2. I'm running the MQTT engine module and the MQTT distributor module. I've got a couple Chariot servers, which is a standalone MQTT server product from Cirrus Link, running each in their own EC2 instance in the cloud, and various devices that Wes just described, both physical and virtual, connected or connecting to those 3 MQTT servers. So if I pull up what we see here, this is the web UI for the ignition instance that I have running in EC2, and I'm on the modules page. So if I scroll down, you can see that we've got a number of Cirrus Link Solution modules. The 2 that we're going to be focusing on are MQTT Engine and Distributor. One thing to note is that our Sparkplug functionality that we have, support for Sparkplug built into these modules, is based off of the Tahu Java library. So that's where our client implementations are actually being leveraged in our products from Tahu. So when you install MQTT Engine, you can go to the settings over here, and we have this servers tab. And we can see that we have 3 different servers defined in MQTT Engine, which are the 2 different Chariots that are in their own EC2 instance, and then the local MQTT distributor server. Right now, MQTT Engine's disabled, so it's not connected to these servers. So in a few minutes, I'll go over here and enable this. But before I do that and actually establish a connection, I want to point out that we have MQTT Engine configured as the primary host. So when it connects to a server, it's going to publish a retained state message saying that it's online and connected to that server, so that any client applications out there that are waiting for their primary host to become connected will be notified and then can publish their berths and begin to start publishing their data. So if I pull up this is Ignition's designer application. So this is where, with an Ignition gateway, you can see all the tags in the gateway and create dashboards based on those tags. Right here, we have a very generic dashboard that will demonstrate when MQTT Engine has seen new devices come online and connect and start publishing data. So if we go over here, we have different tag providers. If we go to the MQTT Engine tag provider, right now it doesn't know anything about any devices because it hasn't connected yet to a MQTT server. And so when it does connect and it does start receiving device data, we're going to get an Edge Nodes folder in here. And because Sparkplug uses the IDs, the group ID, Edge Node ID, and device ID, MQTT Engine can then take those IDs and build up a folder structure to organize the tags and the devices and edge clients that are publishing data in a way that is predictable, so that we can design generic dashboards here in anticipation that devices are going to come online and start populating MQTT Engine with tags. So this dashboard you're looking at right here was designed beforehand to be able to display all the devices that are going to show up here once MQTT Engine connects to a server. So I go back and enable MQTT Engine. I'll go over here, and it went out and connected to those 3 MQTT servers. And now we're going to start seeing devices populating here. So these little dots are actually representing the devices that are publishing berths into MQTT Engine. Take a few seconds. There we go. So now we have 700 in about 10-15 seconds. MQTT engine now knows about 709 edge nodes and over 1,400 devices. And if I go over to the tag provider, refresh it, we see this edge nodes folder. And now we see all these different group folders representing the different devices. So I can look and see we have a group folder with a device for an Ignition Edge client that's out there publishing. We have a Moxa group folder for a Moxa 8100 Things Pro device that's out there publishing, and it's connected to 5 different PLCs. We have a couple Opto 22 groove boxes out there. These swarms are a ton of different simulated directors that are publishing RBE data. And they're connected across the 3 different MQTT servers that we have defined, the 2 Chariot and the local Ignition. And so one thing I would like to show is, since we have all these different clients, and I have a screen right here that shows those connected clients and their distribution across those MQTT servers. So we've got 206 clients on one, 304 on another, and then 200 connected to the local distributor. Since MQTT engine is connected as a primary host, if I were to bring down one of those MQTT servers, then we'd want to see all of those clients walk to the next server and reconnect and see that MQTT engine is connected so they can resume publishing their data. So if I go to the configuration for MQTT distributor, which is our local MQTT server, and I disable this, which will bring down the server, then we're going to see 200 of those devices go offline. And then as they're walking and reconnecting to the next server, they're going to come back online. Now, one thing to note, one of the most important things, I think, is that MQTT engine, like I said, didn't know anything about any of these devices. So all of these devices came online, and in about 15 seconds, we had over 1,000 devices with their tags. Each tag has metadata associated with it, complete tag configurations. So what we're seeing is the edge clients are the source of truth, and all those tags are configured at the edge. And in 15 seconds, they're completely populated in our MQTT engines, this Ignition instance. And in a traditional SCADA system, you'd have to configure all those devices at the edge, and then in order to do anything with them on this side, you'd have to completely reconfigure all these thousands of tags on this system. But utilizing Sparkplug and how Sparkplug describes the data and maintains its session awareness, it is able to basically self-describe all of the data and allow our client application here to visualize it all without any configuration. So that's many hundreds of man hours potentially, depending on how many tags you might have to configure on this side that you're saving. So I want to go and look at this particular Moxa Things Pro device. I have a dashboard created to represent the tags for that. So it's connected to these 5 IOLogic Modbus TCP IO modules. So we've got our Moxa gateway here connected to these PLCs. A couple of these PLCs are publishing analog inputs that are floating by a bit, so we see a steady stream of data being published by these ones over here, whereas these have some relays and digital IOs that aren't changing, but I can actually write to those. So if I were going to write to one of these, we click on here, and what's going to happen is all of these widgets on here are all tied to tags representing these PLCs over here. And so when I change the value of one, MQTT engine is going to take that tag change, and it's going to create a device command message via the Sparkplug message type. It's going to publish that device command, and then the Moxa 8100 is going to receive that, go and actually change that relay, and then it's going to publish a new D-data message representing the new value of that relay and publish it back up, and then we'll see the tag change here on the engine side. So we send out a command to write. We don't update the tag yet, but when we get that confirmation that the data has changed from the edge device, then we'll change the data here. And since at the edge in this PLC, the relays are tied to the digital I/O, we're going to see this corresponding digital I/O point change too. So I'll click on this. Sent the command, and when you saw it change is when the D data was received from the edge device. So let's kind of back down to the device and back message flow. Additionally, we have this relay 4 connected to an Ethernet switch. So when I disable this relay, it's going to disconnect this Ethernet switch, causing these two PLCs over here to become disconnected from the Moxa 8100. So what the Moxa 8100 is going to do is it's going to publish DDEF messages corresponding to these two devices, so that back here on the host application, we can see those death notifications and stale all the tags associated with these devices, because we know that they're no longer connected. So when I click this, it disconnects that, and then all the tags associated with these two devices go stale. So all the tags over here are stale. And we won't be updating, and we consider this data pretty much invalid until we get a new berth that describes the new updated values for all of these different tags. So if I reconnect these PLCs are going to reconnect to the Moxa device, and it's going to publish new birth certificates that contain all the latest values. Now it's reconnected, and we can go back and actually look at some information on these devices to see that they've published 3 different births. I drag that over. There we go. And we have we track in MQTT Engine some of this life cycle events, like the birth count, death count, and such. Now, if I go and look at another edge device, we have this Ignition Edge gateway. And it's connected. So this Ignition Edge instance is running on a Raspberry Pi, and it's connected to a Click Modbus PLC, as well as it's connected to some machine type edge nodes that are, or devices that are being emulated in a Node-RED application on another Raspberry Pi. I'm going to actually show this Click Modbus PLC, though we have a little dashboard to demonstrate that. So this Click Modbus PLC has got a tank tag that's got some metadata associated with it. So the tank here is tank 15. It's got a value of 25.6. And those are 25.6 cc's. It's got a range. It's got a documentation for that it's representing fuel. All of this information around this single tank tag is published in the berth to describe this tag for this Modbus Click PLC. So since this is Ignition Edge, I can pull up here, and this is a web UI, the Ignition web UI for that Ignition Edge device running on that Raspberry Pi. And this is the modules page. So similarly to how we showed the full-blown gateway, we can see that this has a lot fewer modules, and it's only running MQTT transmission. So on the edge, MQTT transmission is taking those tags and converting them to Sparkplug messages and publishing the data up to the MQTT server, and then MQTT Engine is receiving it. And so we see the designer for our central gateway, and then we also have a designer view into the tags at that edge on that ignition edge instance. And so I can show those, and we see those over here. So if a tag changes over here, it gets published up, and we see it in our central gateway over here. So I can change the pump control, I can disable it, and it stops, and over here we see that the pump control stopped. We also have an expression tag for the status that's tied to the value of that pump control tag. So I can enable it again. Additionally, I can look at this tank 115 tag, pull up its, popped on a different screen, pull up its configuration, and we can see that it's got a numeric range, and say we wanted to change this numeric range. We wanted to set the high, instead of 40, we wanted this tank to go up to 30. Got there. Engineering units high of 30. Say we wanted to change the engineering units to something else, I don't know, kilograms. It doesn't have to be relevant for this demo. And then instead of fuel, it's gasoline. So we changed some of this configuration around this tag. Say okay. So now we want those changes to take effect and actually be published. So we want transmission to publish a new berth with all the tag configuration that we've just finished configuring here at the edge. We can go over here to this transmission control refresh tag, click that, and transmission will rescan the tags and republish berths for its tags. And then over here on the central gateway, since we have this screen tied to the different metadata associated with the tag, we saw that now it goes to 30, it's gasoline, it's got a 19.2 kilograms, and we see all of that metadata change. And that's kind of shows how powerful it is to be able to have all that information defined in one place at the edge, and then have a way of describing it and publishing it so that it doesn't have to be defined in more than one place. And that's pretty much wraps up the demonstration. I can hand it back over to Wes at this point. And I can still share my screen as well. So.
All right, thanks, Chad. So this is just one final thought that we wanted to share. So initially, there was the Internet of People. I know Mike Milinkovich just posted a blog about the LAMP stack, so sort of the origins of the Internet of People. Two big components of that were HTTP and HTML. So HTTP is obviously the protocol, and HTML was really sort of the defining language for how the internet worked, and still is today. So with the Internet of Things, there was MQTT, but there really was no corollary or way for clients and servers to communicate with each other. So that's really what Sparkplug is. It's a definition because it was not included in the definition of MQTT. It's something that anybody implementing an MQTT solution needs to do. So we've done that here with Sparkplug and made it available. So with that, thank you. And then I think there are probably some questions.
Well, at this point in time, we don't have questions yet in the chat. So if any attendee has questions, please write them in the chat, and I will share them with our speakers. In the meantime, well, thank you very much, Wes and Chad, for this really, really interesting presentation. And the demo was really showcasing what you were saying in the slides before. So that's really, I think, an interesting value proposition there for sure. I have a question on my own there. So what could we say in a succinct fashion are the advantages of Sparkplug as a specification and Tahu as an implementation over what we could call plain MQTT, so to speak?
So I think at a basic level, as I showed in one of the slides early on, is that if you don't start with Sparkplug, you have to create or answer a lot of the questions that Sparkplug already answers. So you have to define what your namespace is. You have to define what your payload definition is. And Sparkplug has basically already done that for you. And in addition, define some of these additional features which take advantage of things like state and also provide redundancy support. So I think that's probably the most important, but I think another one in terms of long-term and what we're really hoping and also what we're seeing in the industry is, as I said, there are lots of OEM manufacturers that are starting to pick this up. And so as a result, it simplifies things at your consuming clients as well, in the sense that you don't have to use one company's implementation of MQTT with their namespace and another one's, because all of those things, if independently defined, do not play well together. And so as a result, you need ideally to have a common language that all of those clients speak.
Okay, that makes sense. And this is a very nice segue into a question that we've got from Alex in the chat. So he's asking, can any standard MQTT client and broker be used with Sparkplug Tahu?
Absolutely. So in this case, the underlying implementation of the client in Tahu is Tahu. So all of our reference implementations within the Eclipse Tahu GitHub repo are based on Tahu. So it's 311 compliant. Every single one of the brokers that was shown in this demo are basically 311 compliant MQTT servers. So yeah, absolutely.
And when we consider the wider so there's another question there. So I will refrain from asking mine. So Amit is asking, will Ignition Designer also be part of Eclipse Tahu?
Unfortunately not. So that's a commercial product from Inductive Automation. I should note too, we're more on the technical side than the designer side. So there certainly are much prettier dashboards that can be built with designer than we showed in this demo.
Okay, that makes sense. And Alex is asking, could you elaborate on what is commercial and what open source? What is open source in Tahu?
Yep. So the two main pieces or contributions by Cirrus Link to Tahu, one is the specification, and the other one are the reference implementations that are there. So everything that is in Tahu is non-graphical in nature. It's really the underlying communication mechanisms that Sparkplug adds on top of MQTT. So everything's command line driven, and there is no graphical component. So everything that we showed in the demo was using Ignition and Cirrus Link's commercial products, but that was really to show how Sparkplug and Tahu can be used, but they're not part of the open source contribution.
Okay, so we could say you are using the battle-proven formula of having the open source core and then building additional value inside your own commercial products.
For sure.
All right, that makes sense. I don't see any more questions in the chat. So unless there's a last minute one, the only thing left is to thank you again, Wes and Chad, for this presentation. And thank you all for attending this virtual IoT meetup. I really appreciate your presence. I hope you will be there for the next one. And if you have any feedback, please reach out over Twitter, over the IoT working group mailing list, or whatever channel is convenient for you. We want to well, have other meetups like that and also improve them over time. So if you have suggestions for topics or whatever, please reach out. So once again, thank you very much. It's been a pleasure to host you, and I look forward to seeing you next time. Thank you.
Thank you.
Yep, thank you.